Now let's apply this concept of dynamic equilibrium in a chemical reaction. In our chemical reaction, I have a gas here which is called dinitrogen tetroxide. This is made from two atoms of nitrogen attached to each other and attached to four atoms of oxygen. Every molecule of N₂O₄ is decomposed in a chemical reaction into two nitrogen dioxide molecules. Every one of them is made from one nitrogen and two oxygen atoms. So every N₂O₄ gives us 2 moles. Every mole of N₂O₄ gives us 2 moles of the nitrogen dioxide gas. And this is a forward reaction. After some time, after NO2 is produced, the NO2, the nitrogen dioxide, starts breaking down again into N₂O₄. Starts joining back again together to form in the backward reaction the N₂O₄ again. So this is a forward reaction in which N₂O₄ is broken down into NO2, and this is the backward reaction in which NO2 is joining together. Two of the NO2 are joining together to form the N₂O₄. What about the concentrations? What about the concentrations? We are combining two of the NO2 to form N₂O₄, or breaking down the N₂O₄ into 2NO2. We can call this N₂O₄ the reactants, and we'll call the NO2 the products. Usually it's like that. The forward reaction forms from the reactants to the products, and the backward reaction goes from the products back to the reactants. Now let's start with our reaction with only reactants. When I started here, I don't have anything except the reactants. So I have N₂O₄, N₂O₄, N₂O₄. So let's say that the container has a volume of 1 liter or 1 decimeter cube, and the concentration is equal to number of moles over the volume. Since the volume is equal to 1, so the number of moles over 1 is equal to n. So we can say that the concentration is equal to the number of moles. If I have 1 mole, the concentration will be 1 molar, 2 moles, it will be 2 molars, and so on. So if we represented every molecule here in the drawing by 1 mole, so I have 1, 2, 3, 4 moles of this nitrogen dinitrogen pentoxide inside the container, and I don't still have any of the NO2 yet. It's not yet decomposed. The N₂O₄ is not yet decomposed, so there is no NO2 formed yet. So I have the concentration of NO2 equal to 0 molar still. After 5 minutes, I will see that I have lost only one molecule, or I will say 1 mole of the N₂O₄. So this is -1. And so I will have only 3 moles inside this liter. So I will have 3 moles per liter, or 3 molar. While this mole, when it is broken down, it formed 2 moles of the NO2, because the ratio is 1 to 2. So every time you break one of these, you have broken this one, you have formed 2 moles of the NO2. So the concentration of it now is 2 moles inside the liter. So it is 2 molars for the NO2 concentration, while the concentration here after 5 minutes, concentration after 5 minutes of T is equal to 5 for the N₂O₄ is 3 molar. So concentration is 3 molar. After the time is equal to 10 minutes, after I see the time is equal to 10 minutes, I will see that I have only 2 molecules. So I will have only, draw this in red. So this is 1, 2, 3, and 4. And after the first one, I have first 5 minutes, I have 3, and then I have only 2 after 10 minutes. So 2 inside the liter is equal to 2 molars. Equal to 2 molars. Here it was 3 molars, and here 4 molars. I can see that the at the same time this is decomposing, some of the NO2 molecules are going to form the N₂O₄, but at a slow speed at the beginning. Then its speed starts to become fast. It will become fast to a certain point, that the rate of the breakdown. So here I will see that the concentration of N₂O₄ becomes constant, still 2 molar here after 20 minutes. So after 10 minutes, it's still here in equilibrium with the rate So it will be still 2 molar concentration does not change. Why is that? Because the speed of the breaking down of N2O4 into NO2 is equal to the speed by which the NO2 moles are going to join together to form the N2O4 molecule. That's why the concentration becomes fixed, both of them, and does not change. In the here it still is at 2 molar, and this one become 4 molar, so it's not changed. At the beginning it was 0 because there was no reactants yet, no products yet, and then it becomes 2, and then it becomes 4. When 2 moles of this one was broken, 4 moles was made, and then after 10 minutes I can see that the concentration is fixed. So what can I say? I can say that the initial concentration of N2O4 was at the beginning was 4 molar, and I will have seen that it has changed. I will have seen that it has changed by time until it reached 2 molar, and the concentration of NO2 at the beginning was equal to 0, and then it become 2 molar, and then it increased to 4 molar, and then it become fixed after that at 4 molar. So what can I say about this reaction? I can say that the reaction has reached equilibrium. So the reaction has reached equilibrium at time is equal to 0 or time is equal to 5 minutes. There is no equilibrium yet. The rate of breaking down of N2O4 into NO2 is faster than the rate of formation of N2O4 from NO2. That's why the concentration of N2O4 is getting less and the concentration of NO2 is getting more. And only the time when it became 10 minutes, so when I reached here the 10 minutes, I can see that the concentration, when I reach here the 10 minutes, I can see that the concentration become fixed, where the rate of the forward reaction become equal to the rate of the backward reaction. And that's true because the X2 is for the N2O4 is being turned into NO2 at the same rate that NO2 is being, or the same speed the NO2 is combining to form the N2O4. And if the two rates are equal, the concentration of N2O4 and NO2 at equilibrium will remain constant. I will see here they are 4 here, and here still 4, and here 2, and here still 2. And if the time increased more than that, and equilibrium is still there, even 30 minutes, 40 minutes, 50 minutes, as long as the reaction is happening, the concentration will stay at 2 molar for N2O4 and 4 molar for NO2. So we can simply define equilibrium as the reaction in which the status or the case in which the rate of the forward reaction is equal to the rate of the backward reaction. The rate of the breaking down of N2O4 into NO2 is the same as the rate by which NO2 are making the N2O4. So rate of forward reaction is equal to the rate of the backward reaction, and this is dynamic equilibrium because that's opposed to static equilibrium. This equilibrium is dynamic. So whenever you come after 30 minutes, 40 minutes, 50 minutes, 60 minutes, the reaction did not stop. It's not static. Static means that there is equilibrium, there is no change in concentrations, but nothing is happening. But in fact, here, as the time goes, this is known as dynamic equilibrium because N2O4 keeps breaking down into NO2, and NO2 keeps forming N2O4 all the time. That's why it's known as dynamic equilibrium. So when I look at the concentrations macroscopically, and macroscopically means something that I can measure or see with the naked eye, I can see that the concentrations doesn't change, but in fact, microscopically, so on the molecular side, there is changes happening. So macroscopically, there is no changes as the concentration is fixed, but microscopically, the molecules are breaking down and forming. So we can say that the reactants are consumed or broken down at the same rate at which the products are being decomposed or reacting back into the reactants. So since the rate of the reactions becomes equal, the concentrations of the reactant and products become fixed. A very big mistake of the student saying always that the concentration is equal. No, the concentration is equal. There is not equal. Concentration of N₂O₄ at the equilibrium is equal to 2 molar, while the concentration of NO2 at equilibrium is equal to 4 molar. So the concentration of them is not equal, but it stays the same. So after 1 hour, it will be 2 molar and 4 molar. After 2 hours, it will be 2 molar and 4 molars. It will never change. Why? The speed of this breaking down is equal to the speed of this combination. Please make sure that you know that we are not speaking about one molecule. We are just representing 1 mole by 1 circle. So when I say this has 4 moles, so this is 1, 2, 3, 4. I cannot draw all the moles. I cannot draw 4 multiplied 6 multiplied 10 to the power of 23. So I'm just representing every mole of the particles by 1 mole, by 1 drawing only, by 1 circle only. That's why I will say that I have 4 here. So 4 moles divided by volume 1 is equal to 4 molar, and here 0 moles and here 2 moles, like that. So I'm representing every circle for 1 mole of the compound, but in fact, if I want to draw it correctly, I would have to draw inside this circle how much? 6.02 multiplied 10 to the power of 23, because this is 1 mole of my substance. So instead of drawing only 1 molecule, I should draw 6.02 multiplied 10 to the power of 23. And instead of drawing 4 circles here, I should draw this 4 multiplied by 6 multiplied 10 to the power of 23. If you are having any confusion about the number of moles or Avogadro's number, you can go back to the videos about the stoichiometry and the definition of the mole. But in the representation, we are just representing 1 mole by 1 circle, because it's very difficult to draw all the molecules. If you are speaking about the mole, it will be an impossible job. So if we looked at a graph of the concentration which is mole per decimeter cube or mole per liter, or what we call molar or M, and this is versus the time. The concentration of N2O4 at the time 0 is equal to 4 molar, as we seen here, 4 and then 3 and then 2 and 2. So I would say 4 and then 3 and then become add 2, while the concentration of the NO2 was 0 at the beginning of the reaction. There was no products, and then it become 2 and then it become 4 and then 4. So at the beginning it was 0 and then it become 2 and then it become 4 and then it become 4 molar, 2 molar, and then it's 4 molar, 3 molar, 2 molar, 2 molar. So concentration is of N2O4 was 4 molar, and then after 5 minutes it decreased into 3 molar because of the decomposition, and then it decreased more into 2 molar because of the decomposition. And then I noticed that at this point, I will call this is the point at which equilibrium happens. Why? This is the point at which the rate of the decomposition of the N2O4 into NO2 is equal to the rate of making back the N2O4 from 2 moles of NO2. This is a forward reaction is equal to backward reaction. So I will say that the equilibrium, has started here. So equilibrium has started here, and I will say that the concentration becomes fixed. Whatever the time goes, now after that, the concentration becomes fixed, not equal, because the concentration here is fixed at 4, and the concentration of N2O4 is fixed at 2. So don't say the concentrations equal, the concentrations become constant. This dashed line dividing between the left and the right is where on the left there is no equilibrium here. So in this area there is no equilibrium. The rate of the forward reaction moving from left to right is faster than the rate of the backward reaction. That's why the concentration of N2O4 highly decomposed into NO2, and the concentration of N2O4 dropped, was decreasing down, and the concentration of NO2 was increasing because the rate of the decomposition was starting faster than the rate of the backward reaction. Now after the equilibrium, the two rates become equal and the two concentrations becomes constant, and although they are always changing, so although the reaction dynamically is changing, as we said, microscopically, on the molecular level, the reaction is happening, the concentration macroscopically on the eye level or in the measurement level, which we call macroscopically, becomes fixed and constant. It's very important to note the colors of these gases because this is what we can see macroscopically. So again, macroscopically is what we can see, and we know that macroscopic properties are not going to change. They are fixed or not changing when we are having the equilibrium. Fixed means the concentration is fixed, the pressure is fixed, the color is fixed. While microscopically, what's happening? Microscopically is what's happening in the molecular level, and this one is changing. So if we have this reaction, I have here N₂O₄ is breaking down into N₂O₄ is breaking down. Let's draw it with the black color. N₂O₄. This is a dinitrogen tetroxide is a colorless gas. So colorless gas, and then this changing into the NO2, which is a reddish brown gas. So reddish brown gas or dark brown gas. And after some time, so at the beginning of the experiment, I see it is colorless. There was no NO2. After a while, the NO2 color becomes to show it is a reddish brown color. And after a while, I can see that the color is, this is the reddish brown. The color becomes constant. What is the meaning that the color becomes constant? That macroscopically I cannot see any changes. So equilibrium has two definitions now. It is the status in which the forward reaction is equal to the backward reaction, and there is no change in the concentrations. And I can say the third thing, that macroscopically there is no change. I don't see any change in color, in concentration. I don't see anything change in the pressure. And microscopically, there is change because the molecule starts to break down and form normally. So N₂O₄ is breaking down into NO2, and NO2 is joining to form N₂O₄ without stop, whatever the reaction continues.